Kolmogorov-Arnold networks are a type of neural network architecture that is inspired by the Kolmogorov-Arnold representation theorem. This theorem states that any multivariate continuous function can be represented as a composition of continuous functions of a single variable and the binary operation of addition. KANs are proposed as promising alternatives to multi-layer perceptrons, which are commonly used in deep learning. While MLPs have fixed activation functions on nodes, KANs have learnable activation functions on edges, or weights. In KANs, every weight parameter is replaced by a univariate function that is parametrized as a spline. The main contribution of KANs is their ability to generalize the original Kolmogorov-Arnold representation to arbitrary widths and depths, making them more applicable in today's deep learning world. KANs have been shown to have potential as a foundation model for AI and science due to their accuracy and interpretability. They can help scientists in discovering and rediscovering mathematical and physical laws.
MLPs are one of the fundamental layers in neural networks, while KANs are introduced to be an alternative of MLP. Let's walk through the difference between these two networks. Both MLPs and KANs are fully connected structures, which means that all nodes are connected to all nodes in the next layer. MLPs have fixed activation functions on nodes. Activation can be ReLU, softmax, or something else, which all nodes share the same activation in the same layers. On the other hand, KANs placed learnable activation functions on weights. In other words, KANs have no linear weight matrices at all. Each weight parameter is learnable 1D, function parameterized as a spline. Instead of using complicated calculations, KANs nodes simply sum incoming signals without applying. Since using spline function, KANs usually use smaller computation graphs than MLPs, while performance is better than MLPs in general. One of the major drawbacks of KANs is computation cost, as each weight's parameter becomes a spline function. KANs may have a higher computational cost compared to MLPs. They have been reported to be 10 times slower than MLPs when comparing them on a CPU. However, it is important to note that the overall capabilities efficiency of KANs can end up being around 10 times faster than MLPs when accounting for the speed at which each model runs at a fixed capabilities level. With fixed activations, MLPs learn the compositional structure, which so-called external degree of freedom. In other words, MLPs can be stacked with multiple layers to have a complex structure to learn the feature. On the other hand, KANs not only learn the compositional structure, but should also closely approximate the univariate functions, which so-called internal degree of freedom. It allows KANs not only to learn the feature, but can also optimize these learned features to great accuracy. Before talking about KAN, Kolmogorov-Arnold representation is worth mentioning. Kolmogorov-Arnold networks are inspired by the Kolmogorov-Arnold representation theorem. This theorem states that any multivariate continuous function can be represented as a composition of continuous functions of a single variable and the binary operation of addition. This means that a function with multiple variables can be expressed as a combination of functions that each take a single variable as input and produce a single output, and these functions can be combined using addition. Kolmogorov-Arnold representation has only 2 layers with limited elements, and it may not be able to apply in machine learning fields. However, KANs generalize the network to arbitrary widths and depths. Secondly, KANs figure out the structures to make machine learning useful or generalizable at all. The shape of a KAN is represented by an integer array where the number n in I position is the number of nodes in the ith layer. For example, we have 2, 5, 1 KAN. The first layer has 2 nodes, the second layer has 5 nodes, and the final layer has 1 node. The node is named as L layer and I position. For example, we have node 0, 1 and node 0, 2 in the first layer. The activation layer is between 2 layers. It is named as the previous layer node with J position. For example, we have activation value 0, 1, 1 for the connection between node 0, 1 and node 1, 1. In KANs, every weight parameter is replaced by a univariate function that is parametrized as a spline. In theory, splines can be tailored to closely match a target function by refining the grid to a very fine level. This allows for the creation of highly accurate approximations to the target function. By contrast, MLPs do not have this kind of fine graining. We can only stack more layers with more parameters in order to improve performance. On the other hand, we can start training a KN with fewer parameters and then extend it with a finer spline without retraining the model from scratch. If we want to fine-grain a function f in a bounded region between a and b with b-splines of order k, it can be augmented by the bounded region from k to b plus k. For example, there are 211 KNs, which means the input layer, hidden layer, and output layer have two nodes, one nodes, and one node respectively. For example, we want to fit a function to the exponential of a sine function of pi times x plus square of y with 1000 data points. The grid points start from 3 and increase every 200 steps. It is very clear that the training RMSE loss will be dropped every time fine graining happens, and the speed of dropping is increasing until the grid points reach to 1000. Actually, there is overfit starting from around step 800 as the test RMSE loss kind of flatten, and going up at around step 1400. One thing worth mentioning is that smaller KNs generalize better sometimes. From another 211 KNs, it shows that the test RMSE loss is even lower than 251 KNs, while the number of grid points is larger. This is the topic pruning KNs, and it will be covered later. For MLPs, L1 regularization is used to promote sparsity in linear weights. However, KNs require two modifications to adapt this idea. In KNs, there are no linear weights. Instead, learnable activation functions replace linear weights, so the L1 norm should be defined for these activation functions. L1 regularization alone is insufficient for sparsification in KNs. An additional entropy regularization is necessary to achieve the desired level of sparsity. To calculate the L1 norm of an activation function, we take the average magnitude over its inputs. For a KN layer with inputs and outputs, the L1 norm is defined as the sum of the L1 norms of all activation functions. Additionally, we define the entropy regularization term to further promote sparsity. When we want to visualize a KNs and understand the relative magnitudes of its activation functions, we can adjust the transparency of each function. To achieve this, we set the transparency of an activation function to be proportional to the value of tan. By doing so, activation functions with smaller magnitudes will appear faded out, allowing us to emphasize and focus on the more important ones. This technique provides us with a clear visual representation of the significance of each function within the KNs. After applying the sparsification penalty during training, it can be beneficial to further reduce the network size by pruning it to a smaller subnetwork. In this case, we focus on sparsifying KNs at the node level rather than at the edge level. This approach allows us to create a more compact subnetwork while maintaining important connections between nodes. By selectively removing less important nodes, we can improve efficiency and reduce computational costs without sacrificing the network's overall performance. A score calculation for incoming and outgoing is defined and considers a node to be important if both incoming and outgoing scores are greater than a threshold hyperparameter theta equals 10-2 by default. All unimportant neurons are pruned. In some situations, certain activation functions, such as cosine or logarithm, may have symbolic representations. The function can be used to set the activation function at a specific position to the symbolic form f. However, directly setting the activation function to the exact symbolic formula may not be possible due to potential shifts and scalings in its inputs and outputs. To address this, preactivations, x, and postactivations, y, are obtained from samples and fit affine parameters, a, b, c, d, to approximate the relationship. The fitting process involves iterative grid search for A and B, followed by linear regression. In addition to these techniques, we offer users additional tools for more precise control over KNs. In summary, KNs are a type of neural network architecture that leverage the Kolmogorov-Arnold representation theorem. They offer learnable activation functions on edges and have shown promise as alternatives to MLPs in deep learning models. KNs have been applied in various domains and have the potential to improve interpretability and accuracy in deep learning.